welcome to the IEEE Spectrum Online presentation, Advances in Electromagnetic Transient Simulations from Antennas to Transmission Lines to Motor Design. I'm Dexter Johnson, and I'll be moderating this presentation. Before we start our presentation, I would like to mention a few housekeeping items. For those of you who want to know if this session will be archived, the answer is yes. It will be archived and will be available for review within about 24 hours and can be found on www.spectrum.ieee.org/webinar. Once the archived webinar is available, a notification email will be sent to all the registrants. Secondly, we encourage questions, and I hope we have time for several, which we'll take at the end of our presentation. As your questions occur, please type them in the box provided on your computer screen on the left-hand side and hit the Submit button. You don't have to wait until the end of the presentation to begin submitting questions. As you look over your screen, you should see buttons that allow you to enlarge the slides if you so desire. About volume control. If you're listening to the audio portion of this event over your computer speakers and you need to adjust the volume, turn your attention to the speaker icon at the top left of the screen. You may also need to adjust the master volume of your computer system. At the bottom of the slide in front of you are a couple of additional suggestions that will improve your viewing experience. Now I would like to introduce our presenter for today. Dr. Doug Cragen is the team leader of the Benchmark and Testing Group at Integrated. He has a Bachelor of Science as a physics major from the University of British Columbia, Masters of Science and PhD in Semiconductor Physics from the University of Waterloo. In the last 20 years, he was an assistant professor at Acadia University, taught and researched at the University of Winnipeg, was self-employed and worked for companies in magnetic shielding interfacing equipment to computers, modeling microwave communication networks, and analyzing test data. In 2001, he joined Integrated, and since then he has worked with scientists and engineers around the world, assisting them in making decisions about how to use software for simulations in diverse electromagnetic and thermal applications. And with that, I will turn it over to Doug.
Hello, and thank you for joining me today in this webinar on electromagnetic transient simulations. When I was given this topic, I hadn't thought through carefully enough, I think, how many different things there were to talk about. So when I began to actually prepare this presentation, I discovered very quickly that my list of things that I wanted to say was far more than I can cover in just 1 hour. So you can see some of the ideas in front of you here that came to my mind. What I decided to do is to really refocus it a little bit from being so broad and say what we will do in this webinar is to do what I like to do. I like to just work with the software and talk about the software. So we will be doing live demonstrations of some specific problems today. You can see the topics there. We'll be setting up a transient for showing how there's actually not a unique steady state for some types of problems. We'll be doing a demonstration of coupling system and circuit with actuator types of models. We'll be showing eddy currents in both motion type problems as well as transient signal problems, and showing a high frequency that is very short time pulse propagation through both a filter or antenna and a lightning strike. We will present these as some specific examples of the many types of things that you may be interested in with transients. I hope that at least one of these will satisfy what you came here for today, but what we are most interested in from this webinar is to get some feedback from the people who attended. We would like to follow up with other more targeted webinars on well-defined topics, and hearing from you what topics you are actually interested in will be very helpful to us in planning for the future. On our website, you can find various quick tools for some useful engineering calculations, and what you're looking at right now is a tool for giving parameters of lossy dielectrics. Now, every dielectric is lossy, regardless how small the conductivity. So while you look at something as a phasor problem at a typical frequency of 60, you'll see that the real part of the dielectric constant is so small as to be neglected. When you look at the startup transient for a problem, you've really got a time constant to consider. And all that the conductivity does is determine how long that time constant actually is. One way to get a rough ballpark of that is to find the frequency where the real and the imaginary part are equal and invert it to convert from frequency to period. And for the properties that I've specified here, you can see that that time constant is approximately 1 hour. If we look at a transient analysis that's linked to this page, you can see the key thing to understand what happens in a simple two-layer capacitor type of model. And that is that what you actually have is lossy capacitors, so that the instant you turn the signal on, the voltage will divide according to the capacitance, that is the dielectric properties. But as time goes on, you'll get charge leak away through the resistances, and therefore the voltage will change. So there's actually two different answers to the steady state problem. There's the instant you turn it on, and depending on the time constant, there's the long term. So depending how good your insulator is, you may actually have the device become a conductive model rather than a dielectric model within the time frames that you're running it. The first model that we'll look at is set up to be very much like the example that you just saw on the web page, but showing a few more things that we can do with a more live demonstration. So you see that two sources have been set up, one for the voltage on the upper plate and one that's a ground on the lower plate. The upper plate voltage is a transient source consisting of just one signal component, and you can see this interface lets you define very arbitrary types of signals, from writing functions to importing a timing diagram to choosing from a variety of standard signals. In this case, all we want to do is to study the behavior when you actually turn the device on. So if you look at this, because our time constants are going to be approximately 1 hour, we turn it on at about 0.02 of an hour and let it rise to 1 volt after that. So if we create a plot to show this, then you can see we start off with 0 voltage. After 1 or 2 steps, it flips up to 1 volt and stays steady there. So the question is, how will the system respond as we proceed? And to map that response, we turn on some outputs. We turn on a contour plot, and we turn on an arrow plot, both of them over the green rectangle that you can see here. As well, we ask to get the voltage at a point in the middle of the device. The materials that were set up were 2 dielectrics. The first dielectric is set up to have a conductivity of 1 to the minus 14 and a relative permittivity of 4. That's the same time constant, the same behavior as you saw on the web page, a time constant of about an hour. The other insulator is set up with the same permittivity, but a conductivity 4 orders of magnitude lower. So when conductivity dominates, the voltage drop is going to be almost entirely across insulator 2. So we can begin running the solver, and you may notice that the default is actually a finite element solver. As a company, we're generally known for our boundary elements, but we really do whatever solver suits a given problem the best. And for this sort of problem, we've determined that finite elements is actually the better solution. Once the model has run, we pop up the output manager so that we can see what's actually happened over these various time steps. And you can see in the message area the history as the program stepped it through 100 iterations over a course of 4 hours in total. So if we begin with the results, we can look at a table that says here is the voltage over these various time steps, 4 hours divided up into 102 steps. And we see that the voltage at the center was initially 0. It then on the second step hit a little over half a volt, and then it rose continually from there. We can copy this data to the clipboard to analyze elsewhere, but we can also just plot within Electro. So what you see here is as soon as it's turned on, because we have equal insulators, equal area, and equal dielectric constants, the instant it's turned on, ignoring signal propagation down the lines, both of them have an equivalent effect, and therefore the voltage in the middle is half a volt. The voltage divides evenly between the parts. But as time goes on, and we see the leakage happen through the more conductive of the two slabs, then we see the voltage at the center rise up towards 1 volt. If we look at the plots, that is plots in the model, on the first step there is no voltage, so we see nothing. We go to the second step, and now you can see a nice color scale, evenly divided again, showing the voltage changing from 1 volt down to 0 volts in the uniform gradient color. And for the arrow plot, you see all these arrows pointing downwards. And the background contour plot kind of ruins the impression a bit, but these are all pretty much the same color. If we turn off the voltage plot, then you can see that more clearly. Now, besides looking at the step-by-step and noting on the scale here what the time is at each step, we can also choose to just animate the problem. So when we click on this button, Animate, what you see is that Electro is stepping through the plots for all the different times that were analyzed. And as you can see a progress bar down at the bottom of the screen. So at the start of the 4 hours, the voltage divides evenly and the field is quite uniform. But as time proceeds, the voltage is mostly over the bottom section, and the arrows change color so that you can see there's very little field in the more conductive region and a much more uniform field in the less conductive region. So that's a very simple illustration in a 2D program, and this can have application, of course, to various types of devices, including capacitive types of devices, transmission lines, and the like. For something a little bit more interesting and that for some may produce a surprising result, here is an insulator like you might see on various types of high voltage transmission lines in different settings. And these kinds of lines can run under many conditions, of course, and they're subject to a lot of considerations that may not be included in a model like this. But one of the most basic considerations is just what effect do the material properties of this insulating material have. And you can see I again set it up with a glass set to have an approximately 1 hour time constant. We won't run the transient in this case, but we will show what the two extreme situations would predict. And that is that if we run the solver, and right now you can see that a boundary element solver is being used because I'm just doing a static solution. We generally consider the boundary elements to be better for that. We're doing a static solution but in permittivity mode. That means that the solution we see is going to be the voltages in the fields that you would get immediately after you flip the switch, that is, turn on however much voltage you've applied. So when we look at the first step here, what we see is voltages and fields corresponding to having permittivity dominate. That is, what the fields will be like immediately after turning the high voltage on. And of the two plots, the one on the left is electric field contours, and the one on the right is voltage contours. So if you look at this, you'll see that the permittivity disturbs the fields a little bit. You can see that the voltage is shaping around the edge of the sheds, but for the most part the voltage dies off quickly right around the actual high voltage plate, and because of that the field is noticeably higher right at the edge of that plate than anywhere else. And there is relatively low fields everywhere around the shed edges. You may notice a blank area here. This is a choice that I made on the scale. Everything that's blank inside is simply higher than the maximum field range that I set, because in order to show on a linear scale the voltage variations, I don't want it to go right up to the actual maximum which exists right beside the plate. So if we consider that's going to be the field distribution due to the permittivity as soon as you turn on the high voltage, the question is, what does it tend towards over time? And that's what we can study by setting the material mode to conductivity. When we get the conductivity solution, we'll see what happens an hour, 2 hours, 3 hours after you flip the switch. So with the output manager, we can examine and contrast both its solutions. Here is step one. This was the permittivity solution, where again the voltage drops mostly near the high voltage, and as a consequence you don't see high fields running down the edges of the insulator. If we go to step two, our conductivity mode solution, now you can see that because the voltage is basically driven by a current that runs down the center, a very weak current, but a current nonetheless that runs down the center, the voltage varies more or less uniformly down the center, and therefore the field is also quite uniform running down the center. And then these sheds that stick out, there's no current running down them, so they will maintain a close to uniform voltage. Therefore, the sheds will push the voltage out. And so you see now the high voltage doesn't drop right around the top like it did. It drops it more or less uniformly from shed to shed to shed. And as a result, the high field right at the edge of the top conductor is not so big. But notice that there are now substantial fields out at the edges of the sheds and as well as in between the sheds. So when you're doing a high voltage insulator sort of analysis in any setting, in this case we're looking at ones you might see along high voltage line, if you're dealing with DC, you have to realize that there are two answers to the static problem. In this case, the conductivity is set to give a time constant of about an hour. So if you were turning your voltage on and off in a time frame of seconds or minutes, probably the permittivity solution is the only thing you'd be interested in. But if you turn this voltage on and leave it for several hours, days, weeks, then it is actually the conductivity solution that dominates. And when you're looking at something like potential device failure, you really need to consider both. You need to consider whether it will withstand the field distribution when you first turn it on, as well as the field distribution over the much longer term. There are many kinds of problems in which the field is time dependent, but where the time dependence is actually related to things like the circuits, the temperature dependence, and the mechanical nature of the device, as opposed to where the field itself is inherently time dependent. So for example, as temperature rises, conductivities change, permeabilities change. You'll see a time dependence to the field, but it's really a thermal time dependence. At any given point in time, in many models, the field solution is still essentially a static solution. Many actuator types of devices like motors, torque couplers, brakes, and the like have this kind of behavior where really you've got the movement of the device means that the field does depend on time because the positions and angles depend on time, and those in turn also depend on the nature of the circuit and so on, and there's even some feedback that takes place. So, for example, as the magnet that you see in the center of this quadrupole device rotates, you'll get different flux linkages going through the poles. Depending how fast it rotates, that's going to lead to a deflux-D time and will induce a back EMF in the coils. So there is a whole circuit dependence because that back EMF will then lead to some current flow and so on. But at any given point in time, at any given angle of rotation, this is actually a static model. And we have various ways that we can approach models of that general type, which do not require transients in the field solver, but do in a more broad sense require transients. The first thing that was done with this model for that purpose was to simply set up and run a parametric. With the parametric, you can vary things like rotation, you can vary current in the coils, and so on. So this particular parametric said, let's rotate the magnet by some amount, and let's compute the flux linkage on one of the coils. Just for feedback, let's produce a B-field plot on a plane that slices through the model. And let's also get the torque on the volume. So once the parametric is run, and I'm not going to run it live for time considerations, we get a table of results. We get a table that says versus angle, we have the flux linkage on the coil, we have the forces on the magnet, and we have the torque on the magnet. So we can go ahead and produce plots such as this one. We have the flux linkage versus the step index, and if I turn on auxiliary axes, that's versus angle of rotation. So the derivative of this curve will give me d flux by d angle, and then if I associate that change in angle with some amount of time, I get the voltage over that small time period. So I can make plots of anything that I asked the parametric to compute, and although it's of no use for this simulation, we can also, of course, feedback other things, watch videos of the shaping of the field as the magnet rotates as well. This is more for just understanding of all the individual scenarios. So it's possible to set up a parametric that will include a variety of currents, angles, and so on, produce a large table of this sort, and then export it. Let's say through an XML file, this button will produce something readable by the Casbach program, or we can just copy it to the Windows clipboard and send it out in general. Besides creating a table of data that could be used by some other software in order to make predictions, it's also possible to link directly to the software. And here we see an example of just a Excel spreadsheet which will rotate the magnet according to some specifications here, 20 steps, 5 degrees per step, and compute the torque on it at every position. So what you see is it's doing the 20 angles of rotation, producing the torque, and then in the end it will create a graph. Now if you think about this, the fact that it's possible to attach and control the program from the outside means that you can actually control it through programs such as Simulink. And this is going to be another webinar that we'll be doing later. We won't go into this in much detail right now, but later on we will be demonstrating how to do both of these sorts of things for actuator types of devices. If we look at the code that's associated here, you can see the basic thing that happens is that we attach to the amperes program, we read the data out of the spreadsheet, perform rotations from 1 to the number specified, run the solver, get the torque, and report it back. But of course we can add lots of details in here to account for things like the nature of the coil, so that we pick up the induced voltage, use that to generate a specified current in the next step, and we can also use mechanical considerations to say, okay, based on this torque, based on friction, based on the moment of inertia, and so on, we'll make mechanical predictions as well. So again, we'll mention all that as possible for now, but there will be a follow-up webinar in a few months which will study this and demonstrate it in more detail for Simulink and for Casbah. When a permanent magnet is near metal, if there is no motion involved, then the magnet will not interact with the metal whatsoever. What you're looking at here is an example of a permanent magnet in the vicinity of a piece of aluminum, and you can see that by all appearances the flux lines from the magnet are passing straight through. So if we look at the physical properties to confirm, we can see that the green bar here is set up as neodymium 45, and the blue shape is pure aluminum. And as I mentioned, as a static model, the flux lines simply appear to pass straight through the aluminum. If we were to furthermore attempt to do something like make an induced current plot on the piece of aluminum in this model, what we see is that there is zero current induced in the aluminum in a static situation. The flux is again apparently passing through. For people interested in the very small diamagnetic properties of aluminum, we do have an option that we can turn on in the physics global, where we include effects due to very small susceptibility, but by default you will see nothing. However, motion changes a lot. As the magnet begins to move, then you will see eddy currents induced in the aluminum because there is now a time-dependent magnetic field. Now, we can do motion in one sense with a parametric. We can go into the parametric setup, create a parameter that will do a displacement or a rotation of the magnet. The problem with that is that it will still only be studying one configuration at a time. It will say if the magnet was here, if it was here, if it was here. There is no time dependence when you do a parametric study. So in order to do a time-dependent study, I have set up another variation of this model. In this variation of the model, if we look in the physics global setup, you'll see that the operation mode is set as rotational transient. And now, if we confirm by the colors again, we still have the neodymium-45 and the aluminum, but we see something new. We see that there is a defined angular velocity on the magnet, and that velocity is 1,000 degrees per second about the origin, which is down around the end of the magnet. So with this configuration, the solver is going to, in time steps, move the magnet into different angles of rotation, and it will track the changes in the flux from one step to another. By doing that, we get the time-dependent behavior associated with the motion of the magnet. So in the solver setup, we can see that there is a transient with a total time given of 0.06 seconds, and it's requested 100 steps to be taken. In the output definitions, you can see that a couple of contour plots have been requested. One related to the magnetic flux lines, one related to the induced current. And once the solver has run, you will see the effect of that. Now you may notice that while our default solver is the boundary elements and we use it for most problems where we can, the default solver for most transient setups is in fact finite elements. And what you see happening here is that every time we rotate the magnet, of course, a new mesh has to be created. So as the solver proceeds, we're seeing the mesh updating. And as the magnet approaches the aluminum, you'll see that the mesh starts getting denser in the aluminum because we'll start seeing more substantial flux changes in the aluminum, d-flux by d-time, and therefore the mesh will need to get much denser there. This is, of course, a very simple model. As for the other examples that we're giving in this webinar, the intent is not to get you caught up in the details of the application, but to be looking at the type of physics and the type of setup that is being done. So now that the parametric has run, we can see that the magnet has rotated by some amount in total, and 2 contour plots are available. Now the outputs were set up to take occasional screen captures of these contour plots. So if we look at step 1, what we can see is the flux lines as the magnet is in the 0-degree position. And you can see that due to the motion, there is already some induced current in the piece of aluminum up here. And if we step through the different plots, you can see that as the magnet rotates, that pattern changes. If we turn on an animation of the results, then you will see the current density in the aluminum increasing as the magnet comes close. And it becomes most intense where the flux from the tip of the magnet is changing the most rapidly. So this model demonstrates for you then how to set up an analysis which involves eddy currents induced by motion. In this case, rotational motion. The Orsted program that you're looking at also has a mode for doing translational motion. When you have time-dependent sources, such as AC voltage or current source, then you will see the magnetic fields generating an electric field, which in turn will induce currents in any nearby conductors. And in a simple harmonic case shown here, what we have is a disk of copper. This is a rotational model So the copper actually revolves around to create a disk over on the other side. And when I put current running through a coil, it generates magnetic field lines in the pattern expected for a toroidal shape. However, the induced current in the copper tends to repel it. So you see the skin effect where the field line is deflected away from the copper. If we look at the real part, then we're seeing predominantly the field that's in phase with the current that's applied. If we look at the imaginary part, then what we see is the flux lines due to the current that's induced in the copper. So this kind of analysis is simply a phasor analysis. It is time dependent, but our focus here is on more interesting time effects than simply harmonic shapes. So having looked at this and looking at it and saying we're working in a time frame with this model comparable to 1/60 Hertz, or roughly 1/100th of a second or so, we created another model based on the same effects, which is using pulses rather than a harmonic shape. The kind of physics that we're talking about here can be applied to many different types of devices, notably where you've got pulsed sources that tend to just turn and off, like when you're switching current on and off in certain types of motors and other actuators, or in different sorts of sensors. So, very common type of source of this, which involves just turning off, is to simply pulse voltages. So here we have a voltage pulse source made up that's applied to the coil. And if we look at it, it was created from two different signals. One signal is a periodic rectangular pulse source with an amplitude of 10 volts. And the other one is just a step source with an amplitude of -5 volts. So the sum of the two is then going to give you -5 to +5, centered at 0. And both of them are set to start on at 1/100th of a second, so that we see a little bit of a lead time. So if we plot just to see the shape, then you'll see that I set the positive voltage to be a much shorter time than the negative voltage. This voltage source, as you can see, is assigned to the coil, and the coil itself can be given a variety of parameters. If you notice here, we can set internal resistances, external loads, and so on. For more sophisticated circuitry, you would need to bring in co-simulation with some kind of circuit simulator, but the basic types of coil connections are all possible within ORSTED. So what is being asked for in this model is two different types of plots. There is a contour plot of the current density that's being asked for on the piece of copper, and an arrow plot of the B field that's being asked for in the surrounding space. Furthermore, three different results are defined. One is the current that flows in the winding, the other is the voltage on the winding, and the last is a field probe, which, as you can see, is right around where the current induced in the plate is going to be the highest. So if we run the solver, you'll see that again, this model is set up to run with the finite elements. And in most cases where we use a actual transient as opposed to a harmonic type of source, then we will use the finite elements. We do have a finite difference time domain solver, which is very useful in high frequency problems. So having run the model then, we can look at an animation of the B field and the J field. And what you'll see here is that the arrows representing the direction of the magnetic field line flux keep alternating because the current is going to flow positive and then negative through the coil as the voltage keeps alternating. And you'll notice that it's not an instant on-off, just like the current that's induced in the plate isn't an instant on-off. There are some time lags involved. And the animation gives you a good sense of this, but the individual results can give you some more specific information. So if we look at the three results, we can present them as a plot. So the plot is very cluttered looking, having three things on it, but if we identify them one by color, what you see is that when the voltage turns on, the current, the black line, goes from 0 and starts rising upwards. And you can see that it's still rising when the voltage turns off. So on this time scale, the current does not actually reach a steady state value. When the voltage reverses, the current drops, and the time is long enough on the -5 volts that it reaches more or less a steady state. And it rises and falls again, and as is very common in pulse-type sources, you see that the very first pulse is a substantially different height than the following ones. So the initial transient behavior needs to settle down somewhat. If we look at the voltage on the winding, then again we start at 0. We've applied 5 volts, but the fact that the B field is changing in time means that we get an induced voltage on the coil as well. So it rises up, and then it decays down towards 5. Again, here you see it gets to 5.07 in the short time frame of the positive, but if we look at the negative, it's gone pretty much back to the -5 volts that was applied. Once again, you notice that the first pulse has a substantially different behavior than the following pulses. Finally, the current at a point in the plate. The current is in response to the time variation. So while the current is changing in the coil is when you're going to see the most current in the plate. So here you'll see that the peak actually corresponds to a point like this. So when the current is turned on, the current in the plate goes down, reaches a peak, and then starts to decay back to 0, because as the current in the coil becomes steady, the current in the plate becomes 0. There is no eddy currents due to a steady state current. The last pair of examples that I'll be showing use our most recently developed program, Chronos, which is a high-frequency or short time frame, time-dependent solver using finite difference time domain. And the first model you're looking at here is a thin dielectric slab with a conductive coating on it. And of course, this could represent various things. This one is titled 3-band stop filter. The basic physics involved here could be indicative of patch antennas and the like. So what this model has been set up to do is to send a modulated pulse starting at one end. And if we skip over to simply show what sort of thing you can get out of a model like this, then as the pulse propagates, we can map out something like the electric field on the top surface of the conductive strip, like I've done here. So you can see that the time being shown right now is 0.04 nanoseconds, and I can manually advance the time. You may notice that I'm using a logarithmic scale because the fields vary quite dramatically from point to point. I can also choose to just let the program animate over time here. And what you see is, of course, as the signal propagates down, the signal divides and it reflects off of the ends here. So you get some very interesting shapes evolving. By doing a Fourier transformation, It's also possible to take your time results and transform them into frequency domain results. So in another tab of our outputs here, we have some plots defined, and here we can show plots of the electric field which are related to specific frequencies, 5 gigahertz, 6 gigahertz, and so on, again by doing a Fourier transform. And of course, other things that are pulled out automatically include numbers like what are the voltages at the ports that are used to define the pulse. The other high-frequency time domain type of model that I'll show very briefly here is simulating a lightning strike hitting the nose tip of an airplane. And the way this is modeled is by treating the lightning strike as a full impulse wave coming down a conductive line and hitting the tip. So once the model has been analyzed, we could again do propagating signals, but this particular solution was set up to show some time domain results. So, for example, a couple of points were selected in the vicinity of the plane, and the question was asked, what is the electric field at those points over time? So when we look at the plots, at the selected point, that as the lightning strike occurs, the electric field rises very rapidly and then slowly decays away. So one can study, for example, what is the interference effect in the vicinity of the plane due to the strike. That concludes the live demonstration portion of this webinar. Again, we would really like to hear from you what topics you would find of interest for future webinars, but for now.
Okay, great. Thank you very much, Doug. Now we're going to take some questions for you, Doug. You there with me?
Yes, I am.
Great. Okay. The first question I have here is, why is voltage waveform not square?
Okay, and I was just reviewing some questions that came in. There's actually two that are almost the same on this. And I think it's referring to when the window pops up showing the actual voltage versus time on the coil when I have an applied rectangular pulse. And the thing about the coils and windings feature, and unfortunately due to the nature of how this presentation is running, I don't have like a PowerPoint where I can just go back to those slides to show, so I need to just describe. But we saw that the voltage overshoots and then decays down towards what the square value would be. And the reason for that is that within the coil, you've got a number of considerations. What the transient signal lets me do is to apply an external voltage, and that is a square voltage. But we can have a multiplicity of considerations on that, one of which may be an external impedance that's part of the circuit, but there's also the internal inductance and the imaginary part of the reaction of the coil to the signal, and you know that you induce a back EMF when the voltage or when the field through the coil changes. So the fact that you're getting a reaction with the eddy currents means that you get an EMF induced in the coil to oppose it, and that adds on to the voltage that we applied, and it decays away. So when you look at the actual voltage on the coil, you're seeing a sum of those contributions, what's applied and what the reaction is.
Okay, great. The next question I have here is, how were you estimating the time step in problems 1 and 2?
Okay. if we go back to the very start of the presentation, and I know everybody can get the presentation to look at later. At the very start, I show a place on our website where we have a few simple engineering tools for estimating and calculating. And the one that I was looking at there was a lossy dielectric calculator. It would tell me for any given permittivity and conductivity what is the real and imaginary parts of the dielectric constant, what's the frequency where those parts are equal, and it also, by inverting that frequency, gives me a kind of time constant for the system, some estimate of what time scales will typically give me comparable effects from the permittivity and the conductivity. So in order to set up a transient problem, once I know that time scale, I simply choose a significant number of divisions, such as 100 that I used it there, but I choose a significant number of divisions spanning a few of those time constants.
Okay, fantastic. The next question I have here is, can high voltage breakdown, or arcing, be simulated?
To actually simulate fully arcing, you would need a plasma type of solver, which we don't provide. But we have a number of customers who work in this kind of area because, of course, that's a very substantial thing within the high voltage industry, issues related to corona, partial discharge inception, and so on. So the quick answer is no, we don't directly simulate that in any way, but the longer answer, which you would need to talk to us about specific needs, is that a number of people do use our software to answer questions that are important to them, that lead them to what they need to know in that area.
Great. So a follow-up discussion might be in order in that one.
Yeah, there's nothing I can say quickly about that other than we don't claim to directly solve it.
Okay, so I encourage the person who posed that question to contact Integrated, then all the contact details are above. Is the conductivity mode solution also done using BEM?
Yes, and I notice there's a number of questions related to the solver choices, which just in the interest of time I glossed over, but it seems to be a large area of interest. So I'll answer this one very broadly, and we'll just see with other questions you might pose along those lines if I feel I've already answered those as well. But in the presentation I talk about 3 different types of solver: finite difference, time domain, finite elements, and boundary elements. And I should also note, for high frequency customers, the boundary element method is also known as the method of moments. And if you're familiar with high frequency software, you may know it under that name. The vast majority of software products like ours use finite elements. And the reason for that is not that it's always the best. There's many types of solvers out there because there's many types of problems, and every solver brings its own advantages and disadvantages. So what we've done as a company is to implement a variety of solvers so that we can advise people based on what we see in the physics of a model, what's the best way to solve it. Now, the finite difference time domain is the easiest to implement and the fastest to run in general, but it's also the most constrained in terms of being able to give good answers. So if you have a relatively easy problem, then finite difference time domain isn't the best solution because the other methods will solve it readily better generally. Finite elements is the nicest trade-off if you're a company developing software, and that's why it's so broadly used. It's a very easy solver to develop. If I was myself to one day decide to go compete with integrated, which I don't plan to do, but if I did, I would probably work with a finite element method as well, because the time taken to get boundary elements working well is very considerable. Our company was founded on the master's and PhD thesis work of a couple of people, and the method had to be further evolved over the first few years of the software very substantially. So the amount of work that you need to do over what's readily knowable in the public domain and what's easy to do is considerable. But that's our problem as a company, not the customer's problem. But what I want to emphasize is you see so much finite elements out there just because anybody who wants to set up a company doing this kind of thing, it's the easiest solver to implement. Now, the presentation that I just did, everything that was solved as either static or as harmonic was done with boundary elements. So what I want to emphasize is that for the most part, those sorts of electromagnetic problems, either static or phasor, are best done with boundary elements in most cases. For the specific case of transients, which is what we're focusing on here, the amount of work that it would take for us as a company to develop actual field transients, and I hope it's clear I was distinguishing here field transients as opposed to, let's say, circuit-related transients or electromechanical or electrothermal coupling types of transients, which on the field side are still essentially static. But actual electromagnetic transients can be done with boundary elements, but it will be a very slow solution. It will be very development intensive for us to provide it. So what we're doing for transient type simulation is to present finite difference time domain and finite element solutions. But where you see all my setups and explanations referencing phasor and static modes, those were all boundary elements.
Okay. Next question is the newly developed Chronos best suited for high-frequency analyses?
Yes, and I'm actually not even sure what's the correct terms here, because Chronos is like our Singular program in that it solves high frequencies, or the way I think about it as a physicist is retardation times or propagation times are significant. That is, when I switch the voltage, by the time I change its value, that information still hasn't propagated across my entire model. Singular is our frequency domain solver, and Chronos is our time domain solver. So calling it high frequency isn't quite right, although I pointed out that by Fourier transform, all the time-related information can be transformed back to give frequency results as well from Chronos. So it's related to high frequencies, but in fact the lightning strike, if I had allowed myself more time to show that in detail, the lightning strike is actually not quite so high frequency for such a short time. When you look at the details of that, the length of that time signal is longer than the time is substantially longer than the time for the lightning strike to occur and for that information to propagate across the plane. So Chronos actually does have what we call a low frequency mode, which just means that the solver is being configured to allow for relatively long propagation times.
Okay. have another question here, maybe one or two more questions. It kind of follows on what you were talking about before, but maybe you can address this particular point, and that is you determined that FEM was best suited for this problem, yet it is linear and bounded with a nonconductor. Why would you argue that FEM is better suited than DEM?
Right, and I think that one came very early and therefore would have been related to the very first problems that I did with the electric insulators. And again, when I did a static solution on those problems, I did use the boundary elements because across the high voltage industry, it's almost always best to use boundary elements as opposed to finite elements. But in the case where I'm actually looking at the transient behavior, which was where I was going with both of those, then the only option there with our present programs is the finite elements.
Okay, I think we have time for one more question, and that is the example models you showed were quite simple. Can you solve more complex geometries?
Of course, yes. People solve extremely complex geometries. For presentation purposes, what I wanted to focus on was the physics and the analysis type. So I didn't want to confuse things by getting people too involved in how does this work, what design features is it showing. I wanted to keep it simple. I also wanted, as far as possible, to show the software actually solve. In a few cases that wasn't possible. The lightning strike on the plane, for example, I just opened up a solved model. But I wanted to also keep the model simple enough. But we have customers running arbitrarily large and complex geometries representing real-world simulations involving hundreds or thousands of surfaces. So certainly you can bring these in from CAD as the most common way and simulate very large models as well.
Okay, great. I think we'll wrap it up there, Doug. Thank you very much. Ladies and gentlemen, we're now out of time, and as I indicated earlier, this session will be archived in about 24 hours on www.spectrum.ieee.org/webinar. And once the archived webinar is available, a notification email will be sent to all the registrants. I'd like to thank Doug for making this such an informative hour, our sponsor, and thank you, our audience, for participating in today's session. We hope you found today's event valuable and will return for future IEEE Spectrum webcasts. Thank you.